For our next talk, I would like to welcome our next speaker, Michael Stewart, and the talk is about Learn Your Neural Net for Great Good. Please welcome Michael Stewart.
All right. Hello, everyone. Hope you all had a good lunch. Title of this talk is Learn You a Neural Net, parenthetically, for great good. So who am I? So my name is Stu, alias Michael Stewart. I'm a machine learning engineer at Opendoor in San Francisco. So Opendoor is a fintech startup. We buy and sell homes online. And our mission is just to make the home buying and selling process radically simpler for Americans everywhere. So we have offices here in LA, as well as in San Francisco and Atlanta. So if you're interested in learning more, definitely come and talk to me afterwards. Cool. So the goal of this talk is to kind of puzzle through the mechanics of a neural net. Here a fully connected, like MLP, a multi-layer perceptron-style neural net, on our way to implementing one kind of in Scikit-learn style, kind of compatible with the Scikit API. So what is a neural net? So Wikipedia, the source of all truth, says that a neural net is kind of a collection of neurons organized into layers. And these layers are kind of connected by synapses or weights that have parameters that we kind of push up and down through the learning process. And typically, these layers are connected through these nonlinear functions that take in inputs and spit out some floating point number. So that's good. But here, this is probably easier to understand. Here is a graphic of one of these fully connected neural nets. Basically, you have some input data. Over here, we have input data M, with M features. It gets transformed through a series of layers, and in the end, we make a prediction. Maybe a number, maybe we're doing regression, maybe it's a classification question, maybe we're trying to predict between dogs and cats. But whatever it is, the kind of the basic structure of these networks is that you have a lot of data coming in, and it kind of becomes more refined over time until we produce kind of a final output. So these artificial neurons, they have edges, and they have these weights for these edges that adjust as learning proceeds. Great, but how do we make learning proceed? That's kind of the crux of the matter here. So almost always, the answer is that we use gradient descent, or some algorithm in the kind of the gradient descent, broader gradient descent family of algorithms. So gradient descent, again, we have Wikipedia, gradient descent is an optimization algorithm. It's an iterative optimization algorithm, and it's used usually for finding the minimum of a function. In order to take a step, to take one of these iterative steps, what we do is we find the gradient, and we go in the direction against the gradient. So we go downhill. And a gradient is just it's kind of an abstraction of derivatives. So if I have a function y equals x squared, and I take the derivative, I'll get 2x. And a gradient is kind of just a vector of partial derivative information. So if I have a function of many variables instead of just one, for each variable that I'm taking the derivative with respect to, kind of on the right-hand side of the equation, that'll be like one entry in my gradient vector. So it's really nothing more than just the partial derivatives for a few different variables, maybe just one, for kind of the information encoded on the right-hand side of our equation. OK, cool. So we're going to do a little data initialization first, not too important. And then this is the problem we're trying to solve. So this is the kind of famous, the XOR problem, XOR problem, where we have, here simple toy data, and the first two columns are of interest. This third column is actually just noise, it's junk. And the first two columns, we see that our output for the very first observation is 0, and for the very last observation, these are kind of our targets. These y's are our targets. And in between, we have all 1s. So the middle four, the middle 4 rows, we're trying to predict 1, and the first and last row, we're trying to predict 0. And the reason these middle 4 rows are 1 is because, again, for these two kind of initial columns, we have one or the other, but not both. So that's XOR. Whereas for the first and last row, we have 2 1s and 2 0s, so those would be 0s. This problem it's kind of a little weird. It's a little wonky, and it's not linearly separable. So a technique like logistic regression in the classification setting wouldn't be able to classify this because of this nonlinear decision surface. And a infinitely complex neural net can learn to approximate any function. This one will not be infinitely complex, but we will be able to approximate this function because those nonlinear functions that the Wikipedia definition spoke of, these nonlinear functions, these nonlinearities, allow us to approximate even these nonlinear decision surfaces. These initializations are for the sigmoid function, also known as the logistic sigmoid function, which is the same function that's used by, for example, logistic regression, and is one of the many quote-unquote activation functions that neural networks may use. And we also have its derivative here, so a little calculus and the derivative of the function. We'll go more into these functions in a little bit. So cool. So we can initialize this. And then, Zor, here's kind of the scikit-learn logistic regression, and it's not going to get the right answer. So in particular, we want 0, 1, 1, 1, 1, 0. And we're not quite there yet. So for the sake of argument, it's true that there are a lot of tricks up a modeler's sleeve, and we can make this linearly separable. So we know that these first two columns are important, and if we take the sum over the first axis for those, do a little trickery here, and then modulo that by 2, this kind of returns the actual the way that we set up y, this kind of gives the answer. So if we do a little feature engineering, then we can get the right answer. So it's not that linear functions are kind of like these helpless models that have no hope. With a little feature engineering, they too can solve the Zor problem. But the goal of this neural network would be to not need any human intervention on this feature engineering, and to kind of learn these learn these subtleties of the data on its own. So that's what we're kind of striving for. So that's good. So what is the easiest way we can kind of set up this problem? I would argue it's a for loop. We can try to make one of these neural nets just proceed as a standard Python for loop and see what happens. So that's the got to start somewhere approach. So that's what we'll do. So we're going to use the sigmoid function as our nonlinearity. It's this function here, 1 over 1 plus e to the negative z, where z is the input to the sigmoid, denoted by a sigma, a Greek lowercase sigma. And we're going to do that just because it's a familiar function that some folks will know, and it has kind of a neat form. So let's look at it. So one thing we can do is use SymPy. So SymPy is a NumFOCUS project, so thanks NumFOCUS. So if we make some function here, this will be a function that takes some free variable and returns, that function we just saw, this nonlinearity. And when we plot that, hopefully, with a bit of luck, so close that parentheses first. And with a bit of luck, we'll see, here is the sigmoid function. So the sigmoid is a curve that kind of goes from 0 to 1 in the output domain. So f of q here goes from 0 to 1. And it's kind of rising quickly around 0, and then it has these very flat tails, off to negative and positive infinity. And we're also interested in the derivative of this function. And the derivative looks like this. So the derivative is positive right around 0, and then rapidly tails off and is very close to 0 everywhere else. So that's kind of what the sigmoid function and the derivative of the sigmoid look like. So with that, let's dive in. So here we have a little data initialization. We have just these are our weights. These are our synapses or weights. And we've initialized them randomly. Because gradient descent is an iterative optimization algorithm, this is an exaggeration, but it doesn't matter where we start. In practice, it matters a little bit, but we can start randomly, and we'll still be able to proceed to the correct answer through this iterative for loop update step. So if we take these random betas, what we want to do, in the end, is take these betas and update them using the gradient information, right? So we want to, LR is our learning rate. It's a parameter that we control. And what we want to do is kind of subtract the learning rate times the gradient. Of course, we haven't defined these gradients yet, but minor technicality. So we actually have kind of two hidden layers here. So we need more layers. And what we're going to do is pass them through the sigmoid function. So we have the sigmoid function we were just looking at. And we want to take the previous layer, basically, the previous layer, and multiply that by the weights to get to the next layer. So we're going to do that 2 times, basically. And this is what's called the forward pass of our model. So forward pass of the NN. And basically, we start with some input, do this kind of this multiply by weights, put it through a nonlinearity. And we can do that an arbitrary number of times, here just 2. And this thing, right, like this is our y hat. This is our hypothesis. So when you've done the full kind of forward pass, where we do this, nonlinearity, multiply by weights, nonlinearity, the ending result of that is kind of our hypothesis. This is, what we're trying to have this spit out the correct, 0, 1, 1, 1, 1, 0 for the training data that we were looking at. In particular, though, this will actually spit out probabilities, not 0 and 1 classifications. It will spit out a number really close to 0 if it thinks the number is 0, and a number really close to 1 if it thinks the answer is 1, because that's kind of how we posed the problem. So we have this forward pass, but we need a backward pass too. So what's the backward pass? Well, it certainly includes updating the weights. So this is kind of the crux of the neural net is these gradient updates. But in order to get there, we actually need these grad 0, 1, grad 1, 2. Where are those coming from? We don't actually have those yet. So some of this will seem a little mysterious, but we're about to go over some of the mystery on the next slide. So what's the loss? Well, this isn't mysterious at all. We say like this is the hypothesis for our network, and we're trying to figure out what the loss of the last layer is. So basically, the layer that is supposed to predict 0, 1, 1, 1, 1, 0. The loss of that is just like, how much did we miss by? So our hypothesis is layer 2, and the true answer is y. So that's our loss. That's pretty straightforward. So great. So we have this loss term. And now this may look a little wonky, but we have this loss, and we have this like sigmoid prime. This is the derivative of our sigmoid function, which we were looking at before. And we can just put layer 2 through there. And then, in order to get the gradient for the kind of those weights, those synapses from layer 1 to layer 2, what we can do is take this layer 2 delta, and well, what else do we have? We have this layer 1. I can transpose that, multiply by delta. I understand this may not make a staggering amount of sense at this point, but we're about to review. So that's one thing we can do, and we can kind of repeat that. So we have this next layer, and we're going to need to take care of it too. This is probably the downside of having all your neural nets be for loops. A lot of copy and pasting. It's probably not what our final solution will look like. But now we have kind of the same setup, but here we're not as lucky. So here this is like output layer loss is easy. It's really easy to figure out what the loss of the output layer is, but it's not as easy for these inner layers. However, we're lucky. We have this layer 2 delta, and it turns out, we have these betas, and we can transpose them, and that might do what we want. So if we take a look at this, we're getting a number really close to 0, 4 numbers really close to 1, and a number really close to 0. So that's good. That's great. If we recall what y looked like, that's exactly what y looked like. So somehow, some way, this like magic calculus stuff going on here seems to be onto something. So let's figure out what this magic calculus is doing. So why is this so? Like why is this a reasonable strategy? Like why is this the kind of the underlying architecture for all neural networks these days? Well, the answer is the chain rule, which you'll hear kind of referred to sort of interchangeably as backpropagation in the context of neural nets. And the chain rule is from kind of high school calculus. And what we have is a cost function. And our cost function is a function of something. And this something, this is our y hat. This is our hypothesis. So if we go backwards, this little ampersand is really, it's really a function. So we could call this z, some function, and close some parentheses, and say, well, what's z? So z is really, np.matmul. It's matrix multiplication. So this still works. And now we can see, we have sigmoid of z, here it's just multiplication, times, something, here like x. So we have sigmoid of z of x times betas. So sigmoid z x betas. And that's exactly what we see here. So, like our cost is some function of our output, our hypothesis, which makes a lot of sense. We want our hypothesis to be as close as possible to the true values. So our cost is going to be some function of like, how much are we differing by? Some function of this hypothesis. So our cost here is kind of 1/2 y hat minus y squared. And if we go back to SymPy for a minute, if we go back to SymPy for a minute, if we have 1/2 times something squared. Here we'll use q again. 1/2 times something squared. That's a parabola. That's a good old convex function. This is a parabola, and here this is kind of change of variable. So this q is really like y hat minus y in this little example, but that's okay. We can use change of variable and call that q, and that doesn't change anything. So if we look at the derivative of this, we get a straight line, and if we kind of see what that means without kind of suppressing the output, we get 1 times q. So basically, when we had 1/2 q squared, we get 1 times q. That may not be a surprise to some folks, but it means that somewhere in the output, somewhere when we do this chain rule calculation, we take the derivative of c with respect to sigma, then take the derivative of sigma with respect to z, then take the derivative of z with respect to w. Because ultimately what we want to do is get this information to w, to the gradient, or through the gradient to w, to these weights. So we have to kind of keep taking the derivative until we get to w. And the fact that we expect to see y hat minus y, that should give us a lot of confidence in this, right? So like here we have one of the 3 terms we were using to compute this gradient. We have this thing, and layer 2 minus y, which is y hat minus y. So those are kind of the 3 mystery terms from calculus we're trying to account for with the train rule. And if we take that kind of through, we'll take the derivative kind of in the mention the form I mentioned, kind of propagating through the functions, the quote-unquote chain, and we see we get y hat minus y times sigmoid prime of z. Z is again a function of x and w, a function of our our layer, or the input to the layer, and the weights, and we also get x. Because that's, when we take the derivative of, a constant times x, you will just, or, w times some constant, here x. When we take the derivative of xw with respect to w, we'll just get x. So those are kind of the 3 terms we're trying to account for. And sure enough, this thing, layer 0 transposed, that's really just x, And, for each layer, we can call the input x here. So this is x. This is sigmoid prime of z, right? We haven't even reduced it. We haven't done any reduction of that. It's just sigmoid prime of z. And here we have, the layer 2 minus y. So the 3 terms that kind of magically appeared here are actually from the chain rule. So that's kind of where this comes from. And when people say chain rule, backpropagation, what they mean is kind of this step, this sequence of kind of mini calculus steps to figure out kind of what form this should take on. And I will say we're being a little fast and loose with, sig prime. This only works because we've already passed, layer 2 through a sigmoid function. But that's okay. That's always going to be the case for what we're doing. So the fact that we have kind of a slightly incorrect definition actually aligns perfectly with what we need to do. So, all right. So this is looking good. This clearly did the right thing. And we now are somewhat more confident that kind of the actual math we laid out is correct. I will say we're going to make no attempt to justify this term. This term is actually, if we just did the chain rule 2 more times, we would see this term, which is kind of how we get the loss for interior layers, for hidden layers. But it's just 2 more steps of the chain rule. So that's great, but like, how do we generalize this? So this worked, but the for loop is probably not the optimal way to do deep learning. So how can we generalize this? One thing we can do is we can have some kinds of functions. So here we are some kinds of layers that encode information about functions. So here, if we have some enum, some Python enum, where we expect a function and a function prime, we can see sigmoid. We know how to do this one, right? So we have sig and sig prime. But we could have another function, maybe the tanh function, hyperbolic tangent function, which is in NumPy. And the derivative, again, being a little fast and loose with the derivative, looks like that. So what is this tanh thing? So we can go back to SymPy. And SymPy also has tanh. And we can plot that. And we see that tanh looks a lot like sigmoid. The difference, though, is it goes between -1 and 1. So that will be important in the future. So whereas the sigmoid function we built earlier goes from 0 to 1, this tanh function kind of looks like a thinner version of sigmoid and goes from -1 to 1. So that's another activation function that we may be able to use in a neural net. So we have these kinds of layers, but now we actually need a layer. So we need some layer class that encodes this information. And one of those things, probably the most important thing this layer class has to do is it needs to know how to go backwards. That's the backward pass that we defined in kind of the for loop neural net. It needs to be able to do the gradient updating. So what it takes is, someone tells me the loss of my layer, this layer. That's just some tensor of some kind. And I want to output a tensor that's kind of the loss of the next layer. So I need to follow this contract. Someone tells me my loss, and then I need to output the loss of the prev layer to kind of like obey this contract. So that means we need to get the prev layer loss. But before we do that, this is the betas update we were doing. So we have these betas, and we want some learning rate. Here it'll be fixed. And we'll subtract off the grad, the gradient. But for that, we need to figure out what the gradient is. And for that, we need to know kind of what we were calling the delta before. Here I called it error signal. Sorry for the change of name, but this is the delta from the for loop. So the error signal is kind of exactly the same as it was before. So it's this layer loss. But now we need to actually do some initialization for this thing. So we don't have all the information we need yet. So if we have an initialization, what are the things we need? Well, someone needs to tell us the kind of this layer. So someone tells us the kind and the shape of this layer. What is my shape? And what I need to do with that information is, I need to figure out what my function is. So the kind has this function. And I also need to know kind of what the derivative of my function is, of my activation is. And then I need betas, right? So I need these betas. And that'll be the same as before. So we have these betas. And with that, we can actually look at what the forward pass will be. So again, we had this forward pass followed by this backward pass. And in the forward pass, we kind of just took in some input, which is another tensor, and return a tensor. And OK, so what did we do? So one thing we need to do is store the input someone gives us. So someone tells me, the input of my neural net, or of the layer to this neural net, and I need to keep that. And then I need to do this, activated. This is my layer passed through the nonlinearity. Before it was sigmoid, so we're doing sigmoid times, z of xb, right? So this is, my function, my input, and, my betas. And then we return that. We return self.activated. And the reason that we needed to do this storing is, if we go back to our for loop, in the forward pass of the neural network, we define things like layer 0 and layer 1. But we actually use those information in the backward pass. So there's information that we discover in the forward pass that actually gets used in the backward pass, which means that when we're doing this kind of layer abstraction to make our neural net more general, we have to keep this information from the forward pass so we can apply it in the backward pass. OK, so we have this information. We've saved the input and the activated during the forward pass. And how do we use them? So the error signal is just as it was before. We had this loss, and we had this function prime before it was sigmoid prime, and we had our self activated, right? So we had self.activated. And then the grad was our input transposed times this error signal. And the prev layer loss was this error signal matrix multiplied with our betas transposed. So that's what we were doing before in the for loop, and hopefully the strategy will also generalize. So just to look at kind of like what are the dimensions of these? Like using the dimensions of matrices is often a valuable way to figure out like kind of what's going on. So this error signal, this thing is like m by k. So say we have m rows, and we're in an m by k layer. So we're a layer that has like k hidden neurons, and we're trying to kind of do this backpropagation of the gradient for my layer, where I'm an m by k layer. So the error signal is m by k, just like the layer. So like the layer itself is m by k, and the error signal is m by k, which is great. The loss is m by k. All of these line up. But the gradient, right? The gradient needs to have the dimensions of my betas, because I'm kind of subtracting it from the betas. So the betas are n by k, and that is because the prior layer was m by n. So to connect this m by n layer to an m by k layer, I need an n by k, kind of like n by k betas, and that means the gradient better be n by k too. And so the input transposed, this input transposed is n by m, and the error signal is m by k. So when we do the matrix multiplication, we'll get n by k, just in keeping with the betas. So that's looking very promising. OK, so now what? If we want to have some neural net, that kind of is Scikit-learn style, so this is base estimator from Scikit-learn. This is a thin wrapper around layer. Really we want layer to do all the work. In particular, the bargain we're gonna strive for here is we want every single method in this neural net to be one line, one line of implementation. All of the work should have been done for us already by the layer class we just defined. So what we take is a list of layers, and we can store that. And that's good. So we have a list of these layer fellows. And that's all we take as initialization. And now our forward, we take some x, right? Someone gives us the x data, the design matrix. And what do we do with it? Well, we're going to return x piped through some functions. So what is pipe? So pipe is just a utility. Pipe is just saying, if I have some data and I have 3 functions, this is equivalent to calling all 3 functions on the data in succession. And the reason this is useful is just to make it easier to apply multiple functions in a row, which we're going to need to do because our neural network has multiple layers. So it's just a utility. And great. So what do we need? Well, we need to go forward. And we have all these layers. So we're done. We just delegate to the layers. They go forward, and we're in good shape. So backward. So someone tells us the last layer loss. Someone tells us, like, when we computed the layer loss of the final layer, that was kind of our hypothesis, which was layer 2 minus y. So that was the last layer's output, and that's always easy. It's always easy to get the last layer's output because we know what we want. We know what we're like spitting out of our network, and we know what the true answer is during training. So it's really easy to get the loss of the last layer. So someone tells me the loss of the last layer, and what do? Well, you can probably see where this is going, but I take the last layer loss, and well, I've got these layers, so I can go backward. But I want to go backward, backward. So I actually want self.layers reversed, because I need to start at the end and go towards the beginning. OK, cool. So now we need a fit. This is like our training step. So we take x again, which is tensor, and y, which is tensor, and we return ourself. We return a neural net. And that means we need to return self. But before that, this is just our for loop. So we have this for loop, and what do we need? Again, we need to go backwards. So this is this backwards is how we update the gradients. So every time we call backward in some layer, it's updating the betas using the grad. So that's what we want to have happen. So we need to go backwards, and we need a hypothesis. And how do we get a hypothesis? Well, that's just self-forward x. So this will get us the output of the very last layer. So to get the loss, that's just self.forward minus y. And then we return self. And this is kind of silly, but we were promised one line. We were promised one line per method. So we're going to get that. So one thing we can do is this is a silly trick, but we can return any of that or self. And so what this does is, any is a function that takes a list, and it returns, whether any of them were truthy. And so backward, backward always returns none. So we're going to go backwards, 60,000 times. We're going to have a list of, 60,000 nones, and false or something, false or anything, is anything. So we're going to always get false and then return self. And this is a silly trick, but hey, it's live coding. What do you want? So we have a fit method now. But we actually, the reason we made this neural net is because we want to make predictions. And basically, we want to take a tensor, x, and return a tensor, which is our hypothesis. But we need one more thing. So if we think back to the neural, the neural net at the very beginning, which was just a for loop, what came out of that neural net was not zeros and ones. It was probabilities. It was a probability really close to 0 that the positive class would be 1, if we wanted to signal a 0 in this, binary classification problem. And it was a probability really near 1 if we wanted to signal that, the neural net was highly confident that the output for that row should be 1. So that means this forward method, it really returns probabilities. So predict prob A, this is a method that scikit-learn, estimators may have. If you look at the logistic regression classifier, for example, you'll see this predict prob A method at predicting probabilities. And that's really just the forward method here. Toy example. This is a toy example. Binary classification. But in this setting, predict prob A is just forward. So with that, we can return x piped through pipe again through predict prob A. Then we need to round those predictions. So we want the predictions to not be near 0 or near 1, but we want them to actually be 0 or 1. And then we want them to be integers, not floats. That's not super important. So if we try to clean this up a little bit, we have these 6 methods. We actually only have 5 lines of implementation, for these 6 methods, because we got one for free. So we have messed up something here, which is to be expected. But really, this neural net is not doing a hell of a lot. We have very, very, very terse methods, and that's because kind of everything is being done by the layers. So this is kind of the promise of neural nets in some ways, is that they're very composable. I have a layer. It does cool things. I can make that play nice with every other kind of layer I can imagine. So all of the actual work is done by the layers, and then neural net is just a wrapper that kind of coordinates things. So this makes it very easy to kind of change things like the activation function, make other changes in the size of the layers, et cetera, the number of layers, because really each layer is self-encapsulating in a really powerful way. So great, does this thing work? Live coding and all. So hopefully. So what we need is to give this thing layers. And we know how to make a couple kinds of layers. We'll start with sigmoid. That's what we were doing earlier. So kind is sigmoid. And the shape, well, before we had this kind of like 3, 4, and we had 4, 1. So we'll try it. We'll try it. And sure enough, right, like y hat equals y. So not bad. So this little neural net, with all 5 lines of implementation, is getting the correct answer. And again, that's thanks not to anything here, not to anything on this screen, but thanks to layer. So kind of an alternate title to this talk is the mighty layer class, because really this layer class is quite mighty. All of the work all of the work of the neural net is encapsulated in this layer. So we're not quite out of the woods, and that's because we have this tanh function. Does this thing work? So far so good. But what happens if I put tanh here, right? Like, this is not going to end well for me. Great, so I got all ones. So what's the problem? So the problem, if we go back to tanh and go back to SymPy, is that tanh goes from -1 to 1, not 0 to 1. So the output cannot be taken as a probability at its face. The output of a 0-1 classification, a probability, a floating point between 0 and 1 can be taken as a probability, but that won't work for tanh because it goes from -1 to 1, not 0 to 1. So putting tanh as one of our interior layers is great. We can do that all day. But if we're trying to do this binary classification of 0 and 1, tanh can't be the last layer. OK, so that's good. We have this this neural net. It's working. Well, not when you have tanh as the last thing. But I want to take a minute to pitch SymPy. So we've been looking at plots from SymPy, and SymPy is a NumFOCUS project after all. And I think SymPy is one of the really underappreciated projects in the kind of the scientific Python space. It's not every day you have to deal with calculus, with derivatives, with integrals. But when you're working with deep learning, you do, sometimes. Maybe not every day, but depending on what you're working on, is really, really valuable to be able to have this tool at your disposal to visualize things like, what does the derivative of the sigmoid function look like? That's sort of non-trivial to do by hand. It's not super hard, but it's been a while since most of us have taken calculus. So having SymPy there is really cool. And I want to give an example. So one of my favorite activation functions to come out recently is this thing called swish, the swish function. And before I introduce it, I want to introduce the relu function. This is kind of the most popular activation function today in deep learning is this thing called the rectified linear unit. And thanks to SymPy, we can see what it looks like. So we need some relu of q. We want to plot that. So what's relu? So it's just this. It's the maximum of 0 and q. So when we plot the relu of q, it's just a straight line at 0 in the negative domain of x, and kind of a straight line with slope whatever in the positive domain. And this turns out to be a really powerful activation function. But it's a little annoying that it's got this silly discontinuity at 0. And it's got an interesting derivative too. So this may be not too surprising, but the derivative is 0, kind of in the negative domain, and then 1 in the positive domain. But there's this other function, this really interesting swish function that I was just talking about, which looks a lot like relu, but has some interesting properties. So the swish function is from a Google paper about a year ago, and swish looks like this. So it's our q, our free variable, times the sigmoid of q times some scalable parameter. So that this parameter is beta. Here it's 1. And it looks like this. It's got this weird kind of negative region here. You don't see that every day. This activation function is not monotonic. It starts at 0, goes down, and then goes back up. That's weird. You don't see that with sigmoid. You don't see that with tanh. You don't see that with relu, certainly. But it's kind of cool. But what's really neat about this is we can take a look at the derivative thanks to SymPy. And it looks kind of like the relu derivative, right? Like the function looks like relu. The derivative looks kind of like relu. But it's not perfect. But we've got this parameter. And what if we play with this parameter? So if, say, beta is 10, now all of a sudden this looks really relu-like. If we get rid of the derivative, we can't tell this is different from relu. So we have this parameter. When it's really high, this swish function looks like relu. And when it's really low, say it's 0, now it's just a linear activation. So we didn't talk about linear activations, but this is also a very useful part of any just straight matrix multiplication is kind of a linear activation. And so we have this swish thing. This is swish. And it kind of interpolates between relu and linear. If if you crank up the beta parameter, or I mean, you can certainly learn the beta parameter too, but if you set a high beta parameter, you get something that looks like, for all the world, like ReLU. And if you set it really low, you get something that's just linear. So it's kind of a generalization of this linear layer and the ReLU layer in this kind of much smoother function than the ReLU. So, well, there's nothing like particular, like, Swish has turned out to be very, very powerful. It's probably underused right now. But there's nothing that important to take away with Swish. What's important to take away with is, SymPy is really cool. If you're working with deep learning, you probably have to deal with derivatives. You probably have to deal with integrals. You should give SymPy a shot, because it really simplifies these things. So with that, I'd like to thank you for your time and open up the floor for any questions. There may be mics, maybe. Or maybe not. I'm also able to repeat questions if I can hear them.
My apologies. I missed the first 2 minutes of your talk. I was obviously late. Can I just ask a question about, did you in fact just summarize pretty much all of deep learning with just NumPy and nothing else?
All of deep learning might be a stretch, but this was our imports. So the only import was NumPy. But we are certainly missing a lot of things. We're missing convolutions, although those are easy to write in NumPy. We're missing recurrent neural nets, although those are easy to write in NumPy. But really, that's kind of what these libraries like PyTorch and TensorFlow are. They're really just NumPy. They're NumPy and then some functions that are wrapping NumPy-like stuff. So deep learning is mostly just matrix algebra and matrix calculus. So in a sense, yes. In a sense, that's what we're aiming for. Sweet. Well, thank you all again.